So this is what it's like inside a neutron star. Now this is formed after a supernova, and effectively all of the protons and electrons are kind of sort of forced into each other to make these neutrons. Loads of neutrinos are kind of given out, and what we're left with is effectively basically one massive nucleus of an atom. You know, it's what a nucleus is without all the kind of space that you get in a normal atom. Now there's some quite amazing kind of facts about what's inside. Effectively, because we've squashed everything, there's no space, and that means that the density of a neutron star is in the region of about 10 to the 17 kilograms per cubic meter. What that means is if you had maybe a teaspoon of a neutron star, okay, so here's just my teaspoon, and here's my neutron star kind of there. This is about 5 milliliters, and you know, in terms of sort of volume, or sort of 5 cubic centimeters, and just this amount of stuff here would have a mass of 2 times 10 to the 12 kilograms. Now that's like 2 with like 11 zeros after it. I'm just going to write that out. That is extremely heavy, and it just shows how dense these things are. Now, the other thing about these, you know, what's left behind after this supernova, this neutron star, is that it's got a radius, you know, in the order of about sort of 10 kilometers, you know, depending on the size of it. And because of the whole kind of thing conserving angular momentum, it also rotates really quickly. And these neutron stars might, you know, rotate maybe hundreds of times a second, and it's pretty incredible. Now, the thing is that, you know, that's kind of what we call a neutron star. But sometimes they get, you know, the mass is so much that actually effectively the neutrons basically get pushed into the other neutrons, because the only sort of inwards force is gravity. And when you've got something which is really heavy, this gravitational force, you know, overcomes the fact that these two things are kind of repelling each other, you know, because they can't kind of go to the same place. And what happens then is when it all goes a bit crazy, and what we then have is a black hole. So a black hole is formed where the neutron star is so massive that gravity pulls everything into effectively one space. And, you know, we've got a certain amount of mass. And what happens is that as everything kind of collapses, the volume of this thing tends towards zero, which means that the density kind of tends towards infinity. And then all the physics that I know, that you know, that we understand, it all kind of stops working, and we have to think about, you know, kind of sort of quantum nature of things, you know, general relativity. It gets really complicated. But black holes do exist. And the thing about a black hole is that, you know, if we imagine that this thing here is my black hole, obviously we couldn't actually see it. If you had an object which was nearby, in order for this object to escape, it would need to have a certain escape velocity. Now, the thing is that not only does it have, you know, kinetic energy in this case, so its kinetic energy is going to be equal to a half mv squared, but this kinetic energy has to be big enough to overcome the, you know, the sort of the potential energy due to this big object here that's got a mass of m. And what we can say then is that in order for this object to maybe escape the gravitational pull of this, we basically need to have its kinetic energy, half mv squared, is bigger than the potential at that point at a distance of r. Now, the thing is that there's going to be a limit here. First of all, there's a limit on how quickly things can travel. And this limit is when the velocity is equal to the speed of light, which I'm going to put down as little c over here. And there's going to be basically a point at which objects, no matter how, you know, there's going to be a radius at which objects can't escape, because they can't travel quicker than this value of c here. And this is what we called the Schwarzschild radius. Now, at this distance, we can basically rearrange this. We can make this value of velocity of this thing equal to c. And what we can then do is equate the two things together. And what we can then say is that a half c squared is equal to gm over rs. I'm just going to rearrange this to make rs the subject. Now, this thing here, rs, the Schwarzschild radius, basically anything which is closer than that, even if it was travelling really fast, it could never have a value of velocity bigger than the speed of light. And that means it would never escape. And, you know, this is quite important. What that means is that around a black hole, which is in this kind of singularity in the centre, there's a certain radius at which anything inside that can't escape. So we're talking about light can't escape, which is why it's a black hole, because, you know, no light's escaping, so it must be black, but also any other information in there. So we don't know exactly what's beyond this point. And you can calculate it from this equation here, that the Schwarzschild radius is equal to 2gm over c squared. Now, c squared is going to be a fixed value, so is the gravitational constant. But what it means is that if you have a bigger black hole, it's going to have a bigger radius at which things can't escape from it. Now, a big misconception that you often see is that, there's a black hole and it sucks everything in. That is not true. Just because this has mass doesn't mean that everything, all the kind of stars and anything nearby all gets pulled into it. Things will still orbit. Just because, like, when this was a star beforehand and it had that mass, things were still orbiting maybe that large star. And in actual fact, even the centre of our galaxy, there's, a supermassive black hole that things in our galaxy, in the Milky Way, are still orbiting around. So things can still orbit a black hole, but we can't see it. Anything in there, nothing's emitted, so no light's emitted, and it's really only as other things, which get a bit too close perhaps, as they spiral into it, they give out radiation which we can detect. So that's a little bit more about the Schwarzschild, I can't say that well, the Schwarzschild radius, excuse my kind of German pronunciation. That's how to calculate it. And that's just a little bit more information about black holes, which can be formed, amazing things. But that's about all you need to know for the A-level course at this time. So, thanks for watching.